This is the night sky as we don't usually see it. Those streaks of light are stars recorded over time. What looks like motion is really the Earth turning beneath them. Come walk with me. In the first season, we followed how our understanding of the universe changed and discovered that most of it doesn't behave the way we expected. To understand why, we need to start with something we thought we understood completely. Everything we can see in the universe comes from stars. Stars are made of ordinary matter, the same kind of matter that makes up everything around us. Inside a star, gravity pulls matter inward, while energy from the core pushes outward. As long as those forces balance, the star remains stable. If we understand how stars work, and if stars are made of the same matter we see everywhere, then that should be enough to understand how gravity behaves throughout the universe. Then we measured how galaxies actually behave, and they didn't match the prediction. Not even close. Stars don't explain this behavior. The matter we can see isn't enough. This galaxy is not behaving the way we expect. Based on everything we understand, it shouldn't look like this. In some regions of the universe, gravity becomes so strong that nothing, not even light, can escape. And this isn't just one galaxy. Across the universe, galaxies form vast structures connected by filaments and separated by enormous voids. Whatever is missing is shaping all of it. But there are also places in the universe where gravity pushes everything we think we understand to its limit. At the center of our galaxy, something extraordinary is happening. Something with enormous mass, a black hole. When Albert Einstein developed general relativity, he didn't think there would be a simple solution. But almost immediately, Carl Schwarzschild found one. It described a critical boundary, what we now call the event horizon. At first, it was known as the Schwarzschild radius. But at the time, no one had ever actually observed a black hole. A black hole forms when enough mass is compressed into a small enough region that gravity takes over completely. Beyond a certain boundary, the event horizon, nothing, not even light, can escape. I remember a conversation I had in the early 1970s with Kip Thorne, a theoretical physicist. At the time, the existence of black holes wasn't yet confirmed, and there were experimental results from Joseph Weber, who was searching for gravitational waves that suggested something extraordinary might be happening. But the results couldn't be confirmed. If those signals were real, it would mean these events weren't rare. They were happening across the universe. If something is possible in this universe, it doesn't just happen once. It becomes common. At the time of my conversation with Kip Thorne, there were other clues as well. Matter falling toward these objects was expected to release enormous amounts of energy in the form of X-rays. Systems like Cygnus X1 became prime candidates. Independent of gravitational wave experiments, these observations were pointing in the same direction. This is an actual image of the supermassive black hole at the center of the Milky Way. It turns out that nearly every galaxy we've studied has a supermassive black hole at its center. But this creates a deeper problem. We've gone from wondering if black holes even exist to realizing they are everywhere. They sit at the centers of galaxies. They shape how those galaxies evolve. And that should mean something important. If black holes are this common, if they are this fundamental, then our understanding of the universe should be complete. But it isn't. There is something missing. Our best description of gravity, Einstein's theory of general relativity, works extraordinarily well. But when we follow it all the way to its conclusion, we hit a brick wall. At the center of a black hole, the theory predicts a point of infinite density, a singularity, and that tells us the theory is incomplete. And yet, at the same time that Einstein was developing general relativity, another framework was emerging: quantum mechanics, a completely different way of describing nature, focused on the smallest scales, atoms, subatomic particles. But these two theories don't connect in the way we would expect. If we scale down general relativity, we do not arrive at quantum mechanics. And if we scale up quantum mechanics, we do not recover general relativity. They are both extraordinarily successful, but they remain fundamentally separate. And yet, to fully describe the universe, there must be places where both apply. Black holes are one of those places. And yet, the universe does not respect that separation. In a black hole, gravity is extreme and matter is compressed to the smallest possible scales. But when we try to describe that reality, neither theory works. General relativity breaks down. Quantum mechanics cannot describe it. And that tells us both are incomplete. There are hints that these two frameworks can be brought together in limited ways, but we'll come back to that. We set out to follow how our understanding of the universe has evolved during my lifetime. And what we found is that most of it is still unknown. Dark matter, dark energy, together they make up the vast majority of the cosmos, and yet we still don't know what they are. We built two extraordinary tools to try to understand reality: general relativity and quantum mechanics. But in the places where answers should emerge, those tools are not enough. And until we can go beyond them, our understanding of the universe will remain incomplete. So where do we go from here? If we want to understand how the universe really behaves, we have to start somewhere more familiar. We have to understand how stars work, because it is inside stars that gravity and matter first begin to push against our understanding of their limits. And that's where we're going next. So, come walk with me.